In our first year Algorithms and Data Structures exam, we usually have a question where we make you pick the appropriate sorting algorithm for a particular situation. And it's always kind of hard to come up with the exact scenarios because the theory just isn't very granular. Here, let's try.
What is the most efficient way to sort 1,000,000 32-bit integers?
Well,
I'm sorry. Maybe
no. I think
that's not a.
I think the bubble sort would be the wrong way to go.
Okay, so not bubble sort. That's a decent start, I guess. But how would you do it? How would you sort this dataset? Let's think about this. We'll assume we have a modern desktop PC. The data is already in an array in main memory, and we're only going to do this once. So 1,000,000 32-bit integers. First of all, 1,000,000 is not that much. This is what, 4 megabytes of data? So depending a little bit on the context, this might not be all that challenging at all on modern hardware. Let's actually try this real quick. See how a standard library fares. Here's Python. We want random numbers. Let's get a list of 1,000,000 of them. Did I get this right? Yeah, and okay, this looks random to me. We want to see how long it takes to sort this. Let's just run it once. Place your bets now. How long does this take? Here we go. That actually took some time. Half a second. But maybe something somewhere needed to warm up. Let's try again. No, okay, that's actually how long it takes, it looks like. This way I'm probably getting a new list, right? So let's sort in place. Maybe that's faster. And no, this isn't really faster. But now the list is sorted. Do you think that will matter? If we try this again, do you think the timing will be different? Think about it. Should it be different? And yes, this is actually much faster. Aha! Was it a fluke? No, it's real. This is actually much faster. So the actual data matters quite a bit, as we see. A completely random list takes half a second to sort in this way on this machine. And if that's the only thing you're doing, that's not so bad. I can wait half a second. But if you need to do this all the time as part of some other algorithm or for every request to the server, that could be bad. You know what? Let's get a second opinion. Here's C++. We want random numbers, lists. We need a sorting algorithm. Don't worry about this. We want 32-bit integers. Okay, now we need to do some typing here because I need to say how I like my random numbers. And it's going to be from the minimum possible 32-bit integer to the maximum possible 32-bit integer. I'm going to want 1,000,000 of them. I'll put them in this vector. And I know how many numbers I'm going to put in here, so let's actually say that in advance and then put all the random numbers in there. We didn't actually measure how long this took in Python, but it looked like it was pretty quick. Let's actually confirm that. Compile it with modern C++, optimizations on. Just making the list takes, pretty much no time, so that's good. Now let's sort it from the beginning to the end, compile it. Okay. That is faster than Python, but it's not completely different. It's 1/10 of a second. That's still a measurable amount of time. It's something that could add up if you do it a lot. Oh, one more thing. Let's see if this also gets faster if the list is already sorted. Let's sort it 100 times. Compile, and that only takes 0.17 seconds. In less than twice the time we can sort this list 100 times. I mean, that's not really what's going on. We're calling sort 100 times. It's already sorted after the first call, so this is a bit of a weird experiment, really. In less than twice the time of sorting the list, we can sort the list once and then, while the memory is probably still fairly hot, sort that sorted list 99 more times. You have to be a little bit careful if you're actually measuring what you're trying to measure, and if that makes sense. And this entire thing wasn't to say that C++ is better or something. The Python was certainly much easier to write in this case. But your language choice can make a big difference. So we did some experiments, some ad hoc experiments to get a feel for the situation. And we already ran into some complications. It made a huge difference whether the data was already sorted. Indeed, bubble sort is efficient on nearly sorted lists, and so is, for example, insertion sort. If you look at the code generated in our small example, you'll see heap sort, something called intro sort, more on that in a second, and hey, insertion sort. Well, would you look at that? That could actually explain why we're so fast on sorted lists. This entire code is a bit much to go into here, but it looks like it uses various sorting algorithms in combination. So what is this intro sort? That doesn't stand for introduction or something. It's not about the start of the list in some way. It stands for introspective sort. In a way, it pays attention to how it is doing. And it was introduced in a 1997 paper by David Musser. The idea starts like this. Actually, quicksort is a really good sorting algorithm. We'd be pretty happy to use it if it weren't for the occasional disaster. Its average runtime on uniformly distributed instances is theta of n log n. Furthermore, it is, in terms of constant factors, faster than most other sorting algorithms on most inputs. The thing that's bad about it is its worst case. It can end up doing a quadratic amount of work, and that's really bad. And not just in theory. Sometimes you just have to sort really long lists, and it can be a big problem if all of a sudden, this one time, it happens to be super expensive all of a sudden. Let's think like a theoretical computer scientist for a second. If you have two different algorithms for the same problem, whose running time behaves differently on specific instances, if they have trouble with different instances maybe, there also exists an algorithm that has, on every instance, the better of the two runtimes. Maybe that sounds kind of magical, but you can just cheat an additional factor 2 in the big O notation. You just run both algorithms. One step of algorithm A, one step of algorithm B, one step of algorithm A, etc. And as soon as one of them finishes, we take its result. The overhead is only a factor 2. So how do we fix quicksort's worst case? Just interleave it with merge sort. Then we'll have the worst case O of n log n. Sure. True, but let's go back to thinking like a practical computer scientist. Merge sort is actually pretty much a disaster on typical computer architectures. If you're sorting small things like integers especially, we probably want an in-place sorting algorithm. But now we have a different problem. If both algorithms are going to shuffle the list, at least one of them will have to do some amount of copying, which is A, expensive, and B, no longer in place. So what is quicksort's problem actually? Well, sometimes it repeatedly partitions the data poorly and ends up recursing lots and lots of time on a part of the list that only gets a little bit smaller each time. One way to address that is to spend some time to find a good pivot, a good element to partition the list on. We can't spend a lot of time on that because, and I'm quoting Musser here, heap sort is only about 2 to 5 times slower than quicksort on average, and it has n log n worst case. To get the good behavior of quicksort, we can't really add much of anything to it in the typical case. And hey, heap sort, we saw that in the disassembly, remember? So here's Musser's idea. We just let quicksort do its thing unimpeded, going on its merry quick way, except for one thing. We keep track of how deep into the recursion we've gone. If this gets out of hand, we switch to heap sort to finish that part of the list in n log n time. Here we use that quicksort partitions the list on its way down into the recursion. Any part of the list that a particular quicksort call is working on is already in the correct place. It's just not internally sorted yet. Switching algorithm all of a sudden in this sublist doesn't disrupt the rest of the algorithm. So by switching to heap sort, we'll pay about a factor 2 to 5 on average, apparently. But we've defended against the disaster case. The runtime of this combined algorithm is, fairly trivially, bounded by O of n log n. And Musser presents experimental evidence that introsort is actually almost as fast as quicksort in almost all cases. And indeed, it kind of must be. Quicksort's disaster case is rare. Otherwise, its average case wouldn't be good. So we rarely have to fall back to heap sort. This entire trick is meaningless in terms of big O worst case. Just use heap sort from the start. But it allows us to get the good case of quicksort. In that spirit, where does insertion sort fit in? We also had insertion sort in the disassembly. Now, maybe you can think about that for a second. Insertion sort is quick on almost sorted lists. Where does insertion sort go in, gestures broadly, this thing? Trying to detect if the array is almost sorted is probably a bad idea, I think. That sounds like it takes a bunch of time that can end up being for nothing. Here's an idea, and this is not actually Musser's idea. He calls it, quote, one of the usual optimizations of quicksort. We'll leave small subproblems for insertion sort to clean up at the end. You already noticed that quicksort's partition puts things in approximately the right place. Well, in the sense that it puts things on the correct side of the pivot. At first, that doesn't say a lot, but as we go further down the recursion, things get closer and closer to where they should be. In a quicksort call from index I to index j, all of the elements currently there are going to stay in this interval. So let's do this. If the interval for a particular quicksort call is below a certain threshold, we do nothing. We just leave it unsorted. And then all the way at the end, after the entire quicksort heap sort hybrid thing, we call insertion sort once on the entire list, which is almost sorted, so that's super fast. If we sorted any part of the list with heap sort, that part is actually sorted and we just run right past it. Any part where quicksort gave up is smaller than the size threshold, so nothing is far from where it should be. Of course, now we need to tune this size threshold, and actually we also still need to tune the recursion threshold. We want it to be O of log n, of course, so we get our worst case bound, but for an actual implementation, we need an actual number. Musser suggests 2 log n for the recursion bound. It's a trade-off between allowing quicksort to do its thing, but catch it before things get real bad. And unfortunately, he doesn't seem to mention the size threshold. But in practice, that's not actually your own problem usually. The standard library implementers will have done it for you. Okay, so that's intro sort, and I still haven't told you the most efficient way to sort 1,032-bit integers. Intro sort seems like a reasonable idea, but maybe you can convince me of something else. And really, it's probably going to depend on a lot of particulars of the actual application that you're writing. Also, this is not the end-all be-all of sorting algorithms. There are explicitly cache-aware sorting algorithms, algorithms that try to space out their reads and comparisons in order to compensate for memory latency in a pipelined processor, all kinds of super cool stuff. This is being actively researched, but I'll leave it at this.